Hey everyone, ever wonder how something like ChatGPT actually reads your words? I mean, how does it understand what you're asking? Well, today we're pulling back the curtain on that very first, absolutely critical step that lets an AI make sense of human language. Let's dive in. So it all boils down to this one big question. You and I, we see the sentence, we get it instantly. But a computer? At its core, it only understands ones and zeros. So how in the world does it go from that binary code to actually grasping the meaning of a sentence? That's the puzzle we're tackling together today. Think of it as a grand translation quest. You see, here's the fundamental problem. We have two completely different worlds. On one side, there's us, with our rich, messy, and super nuanced language. And on the other side, you have the AI, the neural network, which only speaks one language, math. Cold, hard logic. So before any AI can do anything remotely intelligent, we absolutely need a translator to bridge this massive gap.
Our quest kicks off with a pretty big challenge. We need to invent the perfect alphabet for the machine. I mean, how do you even begin to chop up our language into little numerical pieces that an AI can actually digest? Trust me, this is a way bigger deal than it sounds.
In the early days, people had a couple of main ideas. The first was to treat every single character, every A, B, C, and every comma, as its own number. You can think of this like building with the tiniest Lego bricks. Sure, you can build literally anything, but boy, it would take forever. The other idea was the total opposite. Treat every single word as its own unique number. This is more like having those big pre-built Lego models. It's fast, but what happens when you need a piece that isn't in your set? You're kind of stuck. And yeah, both of these early ideas had some pretty major flaws. The character-by-character approach, just way too inefficient. For an AI to understand a word like understanding, it has to process 13 different pieces. That's a huge amount of work. And the word-level approach, it's just too rigid. You get this thing we call a vocabulary explosion. With over 170,000 words in English alone, the list becomes enormous, and it still wouldn't know what to do with a typo, new slang, or a word it's never seen before. And that brings us to the Goldilocks solution, the one that's just right, and it's called tokenization. It's a really brilliant idea. Instead of tiny characters or huge words, it splits text into these handy subword units. So super common words like the or cat might stay as one piece or one token, but a rarer, more complex word like understanding gets cleverly broken down into meaningful chunks like under, stand, and ing. It's the best of both worlds. So you're probably wondering, how is this custom dictionary actually built? Well, it's all done automatically by a clever algorithm called Byte pair encoding, or BPE. It's pretty cool how it works. It starts with just an alphabet of single characters. Then, it scans a massive amount of text and finds the most common pair of characters, let's say T and H, and merges them into a brand new token, TH. And it just keeps repeating this process, merging the most frequent pairs over and over until its vocabulary hits the perfect size. It's basically a self-organizing system that creates the most efficient alphabet possible. Okay, but why should you actually care about tokens? Because they affect you directly, probably more than you think. When you hear that a model has a 128K context limit, that's 128,000 tokens, not words. When you use an API and get a bill, you're paying per token. And get this is exactly why a super smart AI can sometimes fail at a simple task like counting the letters in a word. It's because it doesn't actually see letters. It sees these subword tokens. Okay, quick recap. We successfully turn our text into a sequence of token IDs, which are really just numbers. But right now, they're just numbers. They're arbitrary. They don't have any built-in meaning. So our next challenge is to turn these meaningless IDs into actual, ideas. The solution to this is a fantastic concept called embeddings. Imagine a giant, incredibly detailed map in many, many dimensions. Every single token in our vocabulary gets its own specific coordinate, its own location on this map. So instead of being just a single number, a token now becomes a long list of numbers, we call it a vector, that precisely pinpoints its location. It's like giving every word a GPS coordinate in a giant city of meaning. And here's the beautiful, simple rule of this map. Things that are close to each other are similar in meaning. That's it. On this map, the word car would be located right next to truck and vehicle, but it would be way, way across town from the word apple. Proximity literally equals semantic similarity. This is how the model starts to understand how ideas relate to one another. This map is so powerful, you can actually do math with meaning. This famous equation is the perfect example. It shows out the relationship, or the vector, between king and man is almost identical to the one between queen and woman. So if you start at the point for king, subtract the concept of man, and add the concept of woman, you land almost exactly on the point for queen. It's mind-blowing, and it shows that embeddings automatically capture these complex relationships like gender and royalty. We are almost there. Our AI now knows what words mean, thanks to our incredible map of embeddings. But there's one final, crucial piece of the puzzle missing. It has no idea what order the words appeared in. Right now, it's just holding a jumbled bag of words with no sequence whatsoever. Just look at these two sentences. They use the exact same words, the exact same tokens. So to a model that only has embeddings, these sentences look identical. But to us, they mean completely different things. One is, a story. The other is, well, it's also a story, but for very different reasons. Word order is meaning, and right now our AI is totally blind to it. The fix for this is called positional encoding. Let's stick with our map analogy. If embeddings gave each word a location in our city of meaning, you can think of positional encoding as giving each word a specific street address. We take the original embedding vector and we literally add a second vector right on top of it. This new vector is a mathematical fingerprint that's unique to its position in the sentence. The first word gets one fingerprint, the second word gets a different one, and so on down the line. So how do we create these unique fingerprints? The original paper that introduced this whole idea used a very clever trick involving sine and cosine waves. By using waves of different frequencies, you can create a unique numerical signature for every single position. This method is brilliant for a few reasons. It lets the model easily understand relative positions, it doesn't require any extra training, and because the waves are continuous, it can even handle sentences way longer than any it has ever seen before. It's just a really elegant solution. And with that, we solved all the initial problems. We have all the pieces in place. We can finally see the entire process of how a computer truly reads, from start to finish. Let's check out the full pipeline. And here it is, the complete journey. First, raw text comes into the system and gets broken down into those smart subword units through tokenization. Second, each of those token IDs is looked up on our map of meaning and converted into a meaningful vector using embeddings. And third, a unique positional fingerprint is added to each vector, injecting that crucial information about word order through positional encoding. The final result of this whole three-step process is what we call context-ready vectors. Each one of these vectors now knows what it means and where it is in the sequence. This is the fundamental input that gets fed into the core of the AI. Before any of the complex reasoning or generation happens, this is what the AI actually sees. So, we did it. We've successfully translated human language into the language of the machine. The AI can finally read. But, of course, that just raises the next big question, doesn't it? What does it do with that information? How does it actually begin to, think? That is a story for our next explainer. Thanks for watching.